Now we see notion of representation, transfer, and adaptation. So transfer of representation is a really basic operation we do with in deep learning. So the idea is that we will train a deep network on a given task, let's say task A, and we have a new task, task B, which is based on data similar to task A. Let's say we are dealing with images. So task A is about some object recognition in some images. And then we have a new task B that is also dealing with images, but possibly a slightly different task, but the same type of images. So what we can do is to say, let's retrieve the representation learned from task A and use it for task B. So the idea is that, you know, we have a model here. So we have the representation learned from task A. And then we say, let's use that for task B. So let's just trash. We will just kind of remove the task A classifier, which are maybe the last or the few last layers of our neural network, and replace that with new layers that are reinitialized from scratch, but are trained with, as input for these few layers, the original representation we've got from task A. And then we will retrain and learn a new classifier for task B, and possibly we can even adjust the representation. So this representation can be frozen or can be adjusted according to task B. So this is what we call transfer of representation or transfer learning. This is a really basic approaches. And like I say, we can fine-tune the representation or not. Usually fine-tuning helps to get much better results in terms of performance. So this is quite standard. I kind of talk about that directly in the previous slides. And you know, when we are dealing with images, often what we use is that we do this with a representation learned on ImageNet. So we just take the big ImageNet dataset that was 1.3 million images used for object recognition over 1,000 classes. And then we take the models that are performing well on ImageNet and we just kind of reuse their representation for new tasks involving images. So this is kind of standard. This is working well. And this is a way of doing deep learning now without having 1.2 million images for a new task. You know, we just take advantage of that big dataset of ImageNet using its representation and then learn for with a few thousands images to do something else, for example. We also have multitask learning, where instead of doing this sequentially, we learn from task A, we use representation for task B. We are learning, in fact, a representation jointly, simultaneously for different operations. So let's say we have two tasks, task A and B, and we just assign two different heads. So we have head for task A and head for task B. These are two classifiers, which maybe have a different number of classes each, but the representation is shared, is common to the two. And the idea is that we train says for a sample assigned to task A. So we will get the sample through the representation, and then it will be geared toward the task A classifier with a decision. And then the backprop will go through task A, and then go through the representation to update these weights. The task B classifier is not modified at all. And then we get a new sample, which this time may come from the task B, and then we go through like the same process, but for task B and backpropagate it and update the weights for task B and the representation that is shared between the two tasks. And so we need to mix the data and mix the task along the training and proceeding in such a way, we can expect the representation to be more general than being trained only on one of these two tasks, because we will kind of learn concepts that are usable for both tasks, which is probably more general. It will generalize better, will be more general than learning only from one task. And it also basically increase the number of the training sets, because instead of learning on one training set, says for task A, we are learning on training sets for task A and task B. So it may allow to get more data. More data means better neural networks that will generalize much better. Another approach in line with that is what we call few-shot learning. And the idea is to say, okay, now we learn. What we saw here was basically a way to learn a representation over a different task. We still assume we have hundreds, thousands of images, for example, or samples for each task. With few shot, we rather say that how can we learn? What can we learn something, or can we learn to learn? I mean, can we learn a way to be effective at processing new concepts with really few instances, really few data? This is the problem we are looking for few shot learning. And it has been kind of formalized as it's a kind of game, or kind of a way of doing it, is to have this n-way k-shot models. So basically we say, okay, we learn something at first, and then we are able from it to process a problem where we are facing like n classes, and in each class we've got k instances. An example here is to say we have n equal to 3, so 3 classes: cars, cats, and meerkat. And then we have 2 samples, 2 instances per class in our support set. So we want to train from that. We basically have 6 instances overall, 2 for each of the 3 classes. And we say from that, we want to be able to correctly process a query set, which is kind of testing set, which include new images from the same classes that we want to classify. So every images in the query set will be classified. We'll just say, is it like from the first, second, or third class? And it will associate it hopefully to the second class, and so on for the other samples from the query set. And the idea is that the model is not necessarily aware of the specific concepts. You know, it is not aware of the cat classes, but it is aware that we've got sample from a class here corresponding to the second, I would say, column in our set here, support set, and it tries to assign the queries, the samples from the query set to the right class in our support set. So this is the support set, which is kind of the train set when we are using that, and the query set is the new instances to process. And the point is that we are learning a model that is dealing with this, that is changing all the time. You know, at once we have a support set with cars, cats, and meerkats. The next support set can be with much different classes. So every support set deals with different classes, which are not predefined at first. And the idea is that we want, in terms of generalization, to be able to deal with new classes that are unseen at all from the model, and for which the model is able to perform well. It is able to process this new data very easily, and it's dealing with new type of classes. So the point is that it has learned what is an image, for example, or what is the general concept which I should deal with for this case, for the context in which it is operating. So a way to implement that, it's not the only way, it's just one of the approach that we can use for that, is what we call prototypical network. So the idea is to, I would say, summarize the support. Remember, the support of a class is basically we have 3 classes, and we say we want to summarize this class with 2 samples into something more general. Likewise for that here. And this is done only by averaging. So we will compute an average value of the prototype, but not in the original space. What we will do is that we will make a mapping. So we will get a neural network that will map the original space in a new space. The space and generated here can be in 2 dimensions or more dimensions, but we want to get a space that is meaningful in terms of classifying with nearest prototype. So basically, it's like a simplified version of the k-nearest neighbor, where we have one neighbor, and in fact, we are not looking at all the samples, but we are looking only at the prototype, which is the average of all the samples for a given class. So here we say we have like the same thing. We have, no, we don't have the same thing. We have 3 classes, 3 ways. So we have 3 samples per class, and we have 3 different classes. And so we are kind of defining the prototype as the average of the 3 samples we have for that class. This is our prototype, and we do this for all the classes. And then we are computing the nearest neighbor prototype, the nearest prototype for our sample X we want to classify. So here we see this X. The nearest prototype is M1, so we will assign X to the class of the green, because it is further away from like M2, which are the red, and M2, which are the blue. So the idea here is that we do this processing this is kind of straightforward. And the learning in terms of few shot for prototypical network is to learn the neural network that will map from images here to some space that looks like that. We also have what we call domain adaptation. So domain adaptation, we use, in fact, we want to deal with the idea of having many domains. So, and we want to use these different domains as ways to better process a new unknown target domain that is related to the source domain. So we want to learn from the source and do better on the target. So what we assume is that the input and outputs are the same for all domains. So we are dealing for the same kind of input, the same kind of output, but we can assume that between one domain to another, there is some shift. You know, we have some differences that are significant to say that these are not the same domain. This can be seen as a special case of transfer learning, you know, where the input and outputs may change in the general case. You know, we get some shift, and as such, you know, we collect data the same way in terms of input and outputs, but the data itself is not distributed the same way exactly. One approach, among many others, is the domain adversarial neural network, the DAN, which has been proposed in part by a team here at Université Laval, which is learning from multiple source domains. So it is based on what we call a multitasking learning models. So we have one head associated to the classification task, and we have a second head that is associated, that aims at discriminating between the source domains in the shared part output. So we want both to be able to classify data from the different domains well, but at the same time, we want to look in an adversarial manner how to identify the domain from which the data is coming from. And as such, you know, the additional head, the head that tries to discriminate between the source domain is making use of a gradient reversal. So we are kind of reversing the gradient to force the intermediary representation to be independent, to represent things the same way. It will kind of abstract the differences between the domain and try to map that in a way that we cannot identify the original domain of each of these samples. And that is to allow to have a really general representation that is not affected by the factor of changes, you know, the differences between the source domains. We want to mask these differences. We want to make it in such a way that we cannot discriminate and say, oh yeah, this data is from like source 1 and this one is from source 3. If we are not able to see that they are different, we can assume that if classification is working well, all the domain differences are hidden and all the specific elements for classification are available. So it looks like this, you know, with a DAN, we have a feature extractor from which we want to extract a representation of X that is general, that is usable for classification, but where the domain differences are not visible, or I would say we cannot be extracted from it. And as such, you know, we have this first head that is trained regularly. You know, we have different data from the different source domains that are classified, and we just try to predict the right label. So it's really classical supervised learning, and we do backpropagation the usual way. We are kind of having some kind of classification loss here, and we just do backprop with the gradient over these parameters and the gradient over those parameters, and that's standard. What is different is the bottom here, where we have this other head, which is not trying to identify the class label, but is trying to identify the source domain label. So we just want to see, okay, this is source domain 1, source domain 2, source domain 3, whatever. And we are using, so this is like based on the same representation we are using for class prediction. And this is trained the regular way. We have some kind of loss over the domain labels, and we want to get this to be as good as possible to predict the right domain. What is special is that gradient reversal here that is kind of flipping the gradient in such a way that, you know, we are backpropagating here, but when we get at that point, we are inverting the gradient in order to train a feature extractor that will try to get the domain predictor to be as poor as possible. So this part tries to figure out the right domain, and this part tries to get this part to be poor. to not work well. So it tries to kind of map things in a way where we will not be able to discriminate between the source domains while being good at classifying the samples. So it kind of steer the feature extractor in a way that it will mask and make the differences between the domain as simple, or as I would say invisible, as much as possible. And that works well in practice. The tuning of the lambda is required because we need to kind of wait between the usual classification loss and I would say the adversarial domain prediction loss. So once we balance this well, we are able to find, I would say, a representation that is doing both, doing good classification while not having capacity to identify all the domains. And then with a new target domain, we should be able to perform well because we expect that this target domain should also be represented in the right way from this process to be usable in terms of classification with relatively good performances.